Hello, good morning. So we finished with the derivation for the columns with all the four conditions. So these are the derivation what we derived for crippling load or buckling load. So for both ends hinged, the equation what we derived pi square EA by L square. One end fixed, other end free, pi square EA by 2 L square. Both ends fixed, say pi square EA by L by 2 whole square. And one end fixed, other end hinged, pi square EA by L square by 2. So if you consider all these things, if you write an equation with respect to effective length, the equation will remain the constant. Like when you consider the denominator, it is the effective length for a particular condition. So for both ends fixed, the length of the column is effective length, that is L is here is nothing but effective length is L itself for both the ends hinged. So when you consider for one end fixed, other end free, the denominator is the effective length. So here it is 2L. So effective length is 2L. So for both the ends fixed, here it is. So that is you can take effective length as L. So L will be equal to L. So L will be equal to 2L. For here, it is the effective length of the column for this condition. Here, L will be equal to L by 2. Okay. So it is for the last condition for one end fixed and the other end is hinged. It is L square by 2. So effective length will be equal to, if you take L, it will be L by root 2. So it is L square by 2. If you do the squaring for 2, that is LL gets square get cancelled. The denominator will be root 2. So you just remember this equation to solve the problem. So we have one more derivation here. So we'll continue with that. So before going to that, we have one more theoretical topic, that is limitation of Euler theory. Limitations of Euler theory. So the general equation for a crippling load or buckling load in all the case when you consider the effective length L. So it is like, so we have the general equation for crippling load or buckling load, that is P is given by, it is pi square EI by L or L square, right? So it is, if you consider the L as the effective length, it is L square, pi square EI by L square. If you consider at any of the case, the general equation, it will be in form of L for effective length, it will be like L square, here also it is L square, effective length L will be equal to 2L. So here it will be L by 2, or here it will be L, L by root 2. So the general equation will be pi square EI by L, that is L square, right? So here the least, the radius of gyration for a, we know the definition for radius of gyration. It is given by, if k is the radius of gyration, radius of gyration, that is k, is given by root of I by a. A is given by root of I by a. So or if you can write equation for I here, I is moment of inertia. So I will be equal to k square into a. So I can substitute I in the above equation. Substitute I in the above equation. So I can get a equation for crippling load, that is P will be equal to pi square E into K square A by L square. Or can rearrange this, pi square EIK divided by L by K whole square. L by K whole square. So this ratio of length of the column, effective length of the column to least radius of gyration, we call it as slenderness ratio. We have done it in the first class in theory class. This ratio is called as slenderness ratio. for a column, for a column. So next, if stress, crippling stress, the equation for stress. If it is crippling stress, it is given by sigma CR. Stress is equal to load by area. So crippling load is P. So stress will be load by area. Our load is equal to stress into area. So if you substitute, you'll get crippling stress equation. This P can substitute this equation. So crippling stress will be equal to pi square E. So AA gets cancelled here. Pi square E by L by K square. So this L by K is slenderness ratio. Definition of slenderness ratio. L by P is slenderness ratio. So we have some limitation for this Euler theory. So this is the general expression for Euler theory. This is the equation for crippling load and equation for crippling stress. So this is the stress equation. So if I look at this equation, the crippling stress, it is given by pi square EI by slenderness ratio. Okay. So if this slenderness ratio increases, if this slenderness ratio increases, the stress decreases. Since it is in the denominator, if this value increases, though it is inversely, it is as this is divided by. So the stress value decreases. As this number increases, therefore, since it is divided, the crippling stress value decreases. So if I can represent that in a graph, so sigma CR, that is crippling stress in the y direction, and slenderness ratio L by K denominator. So what happens if this number goes on? Okay. So when you plot a graph for this, so we'll have a graph something like this. We'll get a curve. So you can look at the equation. So when this value for slenderness ratio L by K increases, L by K increases, so it is obvious from the definition of the equation, the stress value is going to decrease. So this is what happening when it is slenderness ratio is increased. So it is maximum at when the slenderness ratio for a column is lesser, right? So when it is the ratio of L by K is lesser, we have a highest stress. So this is a crippling stress. So somewhere here, so this is sigma CR. So this is the crippling stress at this least value of L by K. So whenever this L by K increase, so the stress value goes on decreasing. So as of for a column with least slenderness ratio will fail more quickly due to this crippling load. Whenever this crippling or buckling load, the column is not stable, it tends to collapse, right? So it is not a case since the column is subjected to so many kind of stresses that it is subjected to buckling load or it may be subjected to a crushing load or combination of buckling plus crushing or compressive load, right? So we cannot operate the column with the least slenderness ratio since the column is not stable due to this buckling load. So the column is always applied with a load. So we have studied that. We studied properties of the material, that is stress strain curve. There is a proportionality limit, that is proportional stress up to when stress is directly proportional to strain. So at that point we call it as proportional stress. So it may come somewhere here, the proportional stress. So this we call it as sigma P. Sigma P is the proportional stress. So we are going to apply the load which is less than this proportional stress just to keep the column in stable, just to keep the column in stable. After this stress, since L by K ratio is very small and the column stress induced will be very high, the column is not stable for least slenderness ratio. So the column is only applied with a stress which is more than, which is less than a proportional stress, which is less than a proportional stress. So just to keep the column in stable condition, so we operate the column below this sigma p, that is proportional stress. Okay, so that is one of the disadvantage of Euler theory, so that this equation holds good only for a longer column. Since the longer column it is only applied with a buckling load, the effect of crushing or compressive forces are neglected in this equation. So it cannot be applied or suitable for shorter column or medium column. It is only applicable or it is only suitable for long column, long column. Okay, so that is the major disadvantage of Euler theory. If it is asked, so it is also asked in two papers. If it is asked for 5 to 6 months, you need to write this graph, show the crippling load and proportionality stress and crippling stress in the graph, and should explain this graph. So that is, if the slenderness ratio is increased, the stress, crippling stress goes on decreasing. So for a least slenderness ratio, the crippling stress for a column is highest. So and column is not stable at a least slenderness ratio. So to make the column stable, the column is only operated below the proportional stress to make the column stable. So, and it is only applicable with longer column, since the equation only tells about, it gives, it takes into account, of buckling load or crippling load. The effect of a compressive stress or crushing stress is neglected by the Euler theory, so it is only applicable for longer column. So that is a major disadvantage of Euler theory. So we have one more small derivation for Rankine theory to overcome this limitation of Euler theory. To overcome the limitation of Euler theory, Rankine and Jordan, by name, Roster suggested an equation which holds good for all the three columns. The column which may be a long column, or it may be a short column, or a medium column, which is subjected to either a buckling load or a crushing load, or combination of buckling and crushing. You can apply this equation that is suggested with a Rankine theory, or we call it as Rankine. Rankine-Jordan theory, or just a Rankine formula. Okay, the limitation of Euler theory, it only accounts for longer column. The long column fails due to buckling load or crippling load. The short column fails due to crushing or compressive stresses, and medium column fails due to both buckling as well as a crushing load. So to account for both the loads, these two have suggested an equation based on all the three stresses. So the Rankine equation, the Rankine equation. So if you consider the notation, if PCR is the crippling load, so for Rankine equation, and PE, if PE is the Euler if PE is the Euler crippling load, so we know that PE is given by pi square EI by L square, right? It is PE or PCR with respect to Euler load. So then we have PC, crushing or compressive stress. Let PE be the crushing stress or crushing load or compressive load. So with respect to the crippling load, let sigma CR be the crippling stress. Let sigma CR be the crippling stress. And similarly, A be the area of the column. If A be the area of column and L be the, so effective length or length of column, effective length or just the length of the column. Okay. Then I and K be the moment of inertia. Let I be the moment of inertia or least moment of inertia, and K be a least radius of gyration. So considering this for notation for the column, Rankine and Euler derived the expression for all the columns. So the general Rankine equation generally Rankine equation. So first one for long column. If it is for long column, the long column fails under a buckling load or a crippling load. So 1 by PCR, the buckling load will be equal to 1 by PE. So this crippling load for a column will be equal to is nothing but a Rankine crippling load, that is 1 by PE. So I need to derive the expression for crippling load with respect to all the three conditions of the column. So if I reverse this, so crippling load for a long column will be equal to PE. So PCR will be nothing but PE. P is nothing but Euler crippling load. So this is for longer column. So since longer column will fail due to buckling load. So only buckling load is considered. Next, for short column, the short column fails under crushing force or crushing load. So the crippling load for a shorter column will be 1 by PC will be equal to 1 by PCR will be equal to 1 by PC. Or the crippling load is nothing but its crushing force that is acting, the force due to crushing. So first you should know that long column fails under which load? The long column is failing only under buckling load or crippling load. The shorter column fails only with respect to crushing or compressive stresses. Then medium column. So whether it is the column is neither short column or long column, medium column. So it is only a medium column. So the medium column will be failing both due to the Euler that is crippling load as well as a crushing load. So therefore 1 by PCR, that is crippling load, will be equal to the sum of crippling load plus a crushing force as well as crippling force. It is going to fail under the medium column fails under both Euler, that is buckling load as well as a crushing load. So we are going to find the expression for crippling load for a medium column. So you just reverse this. or you can take the LCM. 1 by PCR will be equal to, this is P into E plus PC is P plus PC, or you can reverse, take the inverse of this, take the inverse of this. So 1 by PCR will be equal to PE by PC. Right? So next, you can take 1 by E outside. So 1 by E outside, and you can reduce this equation. So just E outside, there is PE. You can take PE outside. So when PE is taken outside, here it is PE one plus PC by PE. So PEP gets cancelled. So expression for critical load or crippling load will be PC by 1 plus PC by PE. Okay. So this PC is crushing load. PC is crushing load. So you know the expression for stress. So this P C can be written as sigma C into E. So it is stress is equal to force by area. So our load is equal to stress into area. You can substitute that. And PE, we know that PE is nothing but pi square EI by L square. Pi square EI by L square. Right? PE is nothing but pi square EI by L square. Substitute that. You can reduce this equation. So PCR will be equal to PC is sigma C into A divided by 1 plus sigma C into A by P into E is pi square EI by L square, right? So now I know the expression for radius of gyration from the previous this thing. So I is equal to, or we know that. So we know that since K is equal to root I by A, I can substitute for I. I is equal to K square A. So therefore, PCR will be equal to sigma C into A plus divided by pi square E A into K square by L square. Or I can write PCR will be equal to A gets cancelled here. Sigma C into A divided by 1 plus sigma C by pi square into E into L by K whole square. So this L by K is slenderness ratio. L by K is slenderness ratio. Or you can write this right here. So this PCR will be equal to sigma C into A divided by 1 plus alpha into L by K whole square. So this alpha we call it as Rankine constant. Alpha is Rankine constant. So that is the expression, final expression for crippling load. So that can be used with respect to any of the column, whether it is a short column or medium column, since it is accounted with stubbornness ratio T. So, and alpha is a Rankine constant. So this alpha is equal to sigma C by pi square into E. So you need to remember this. So remember this equation and alpha equation. Okay. So and another four equation what we done the derivation in the last classes for all the four conditions of the column. So if you can remember that 4 equation plus these 2 equations. So you can solve the problem. Okay. So we'll solve the problem on this. So note down this equation. So one equation here, another one is here. So constant for Rankine constant. So you need to remember this. So 4 plus 2, 6 equations to be remembered to solve the problem on columns clusters. So if it is asked to derive the Rankine equation for a column, you should do it up to here. So for a short column, for a long column, and for a medium column. Okay. So I'll solve the problem in the next class. So do remember the equation. So maybe you'll get you may get the derivation, or else you'll get a problem.